Hello, 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 hello. Guys, how have you been? Okay,
Mr.
I
New.
hope excellent, better than this morning. Thank you so much for asking me. Okay, still remember your question. Okay, what's the problem number? Uh,
Number two.
Jesus, sorry. Let me read
Bless you.
my. Thank you. Just let me. Hey, come on, guys. Please turn on the cameras. Thank you so much, Daniel, for turning the camera. The rest of the people. Thank you. Okay, let me looking for with them in the WhatsApp group. Okay, and let me see what we got. The problem number two. Okay, how many grams of iron at 20 Celsius degrees must be heated to 1 Celsius degrees in order to be able to release 1,180 calories of heat as it returns to its original temperatures. Well, actually, in this case, Daniel, the only thing that we have to do is looking for the quantity of mass. You don't need to complicate it that one, but that's going to solve it. This one, all right. Let me change the camera view. Come on, Sofia, Marcela, Camila, Ricardo, Eduardo, Claudio, Ivan, Mesto, Jerónimo. Please turn on the camera, please. Come on.
Mister,
Uh-huh.
I have an excuse to have my camera off.
Okay then. But thank you so much for letting me know, Amber. And the rest of the people, come on, Marcela, Claudio, Ivan, Mesto. Come on, turn on your camera. Come on, you can do it. Turn on your camera. Okay, let me pin my video and let's see. Yeah, all right. This is geometry. I'm going to move the camera over here. Okay, and that's going to solve the problem. Okay, just hold on a second. Hold on, hold on, hold on. Just like review, we're going to do this example like example number one. I know we're to study a different lessons today, right? But this could be a good chance to repeat a little review. Okay, in this problem, in the example number one, or the problem number two, the homework says, how many grams of iron, how many grams of iron, okay, how many grams of iron at 20 Celsius degrees, at 20 Celsius degrees, must be heated, must be heated, must be heated to 100 Celsius degrees, to 100 Celsius degrees. In order to be able, in order to be able, in order to be able to release, um, 1,800 calories, 1,800 calories of heat, okay, of heat as it returns, as it returns, as it returns to its original temperature. Okay, this is the original temperature. In this situation, I know it could be causes a little bit confused why the problem says. Okay, the problem mentioned how many grams of iron at 20 Celsius degrees must be heated to 100 Celsius degrees in order to able release 1,800 calories. And okay, and that returns original temperatures. Well, actually, in supplementary words, they're asking only for the mass of the iron. So, according for the data, first of all, The problem gave us the quantity of heat. That will be 1,800 calories, okay? And we know what will be the specific heat of the iron. Would you like to give me a hint? What will be the specific heat of iron? Because we're talking about calories, please give me the value in calories. Give me a hint.
0.113.
0.113.
Yes.
Okay, just like this one. Okay.
No, 13.
30 o 103 entonces. Okay, okay. 0.113.
Yes.
Okay, calories, grams, Celsius degrees. And you know, the change of temperature, that will be the difference between the initial and final temperature. You know, 100 minus 20 will be 80 Celsius degrees. And we're talking about what will be the quantity of mass, okay? This is going to be what the values of this problem. So as soon as you can see, the quantity of heat Q will be equal MC delta T. So Q divided by L, Q divided by C delta T. And this is going to represent the mass of the iron. You know, 1,800 calories divided by the product between 0.113 calories, grams, Celsius degrees, multiplied by 80 Celsius degrees, and this is going to be the value from mass, okay? Give me a hand. What will be the value from the mass of the iron?
199.1.
199.1. Okay, that will be grams. And this is going to be the solution set to that problem. Okay, is the problem number 2 the homework, but because we are starting from a review for the chapter, that will be a nice, just for standard warming engines. All right. So let's see, let's going to proceed to solving another problems. Just hold on a second. Let me see the class textbook. Remember, the class textbook will be located in the Google Classroom Planner form. Just let me show you again. Yeah. If you see, this is physics, Google Classroom, trabajo en clase. And the last one, we got class textbook. You push the button over here, push the button once, and you're going to see the PDF format. Well, it's taking a little bit longer to charge in, but you know, this is the internet connection, okay? And this is the textbook that we are using in the class. So we'll bully college physics, real physics. No, we are not playing with physics, guys. We are doing the real physics, okay? And you know how you can find out the physics, okay? Let me looking for the chapter. En la computadora yo ya lo tengo descargado, pero como no estoy en mi computadora, entonces me cuesta un cachito más de trabajo llegar a donde están los ejercicios. Por eso, pero ya vamos a llegar. Son 16.
Miss,
Ajá,
una pregunta.
pregunta.
Si yo puse 0.11 y me salió como un poquitito más, en vez de 0.113, estaría mal.
No creo, no creo que varíe tanto. ¿Cuánto le da la respuesta en esa variación?
204.
No, vamos a pelear por eso, porque como es una pequeña variación por eso, pero no se
Sí.
preocupe.
Gracias.
Aunque lo ideal es para un futuro, cuando ustedes utilicen los calores específicos, usen los valores exactos, ¿verdad? Que es lo que les da la tablita. Por eso es que la tabla de que tiene este libro, ¿verdad? Entonces trate de sacarle copia. Saque copia, no sé, le tomo un screenshot, ándelo en el celular, donde usted sienta que sea más práctico, ¿no? y después de ahí lo mantiene en el alcance de su mano. Muy bien. Yo sé que este tema de calorimetría, yo creo que ya lo vieron con mi Isabelar, ¿no?
Sí,
¿Aló?
un poco.
Sí, un poquito. Lo único que ya vamos a llegar a lo que ustedes están viendo con ella, lo que es los cambios de fase. No crea que no se miran en física, sí se miran. Solo que ahorita los estoy llevando un cachito con cuidado, ¿verdad? Ok.
Mister, aunque
Ajá.
en la tabla del libro dice que el color específico de iron es 0.107.
Ah, y aquí 113. Bueno, como le digo, son pequeños detalles. Pero en fin, pequeñitos, bueno, no importa, pero nos vamos a basar en la tabla del libro. Ahora, si hay una pequeña variante, entonces yo les estaría dando en el examen, yo les estaría dando el calor específico. Si considero que hay una variante más, ¿cómo sería la palabra? ¿Cuál sería la palabra más, una variante significativa? ¿Ok? Let me looking for a single example. Okay. All right. With the last class, we solving that one. Hmm. Yeah, this is going to be a good one. Okay, the example number 2. Da, 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 da. If you cannot see or read the problem, guys, and the moment I'm going to write in the whiteboard, let me know because I'm using the platform, the Google Classroom, to see the textbook. Okay, so give me a hand, just in case you cannot read the problem. All right. So the problem number 2, we're going to use this one. A unknown substance, a unknown substance. Okay, a unknown substance has a mass of this case will be 0.125 kilograms. Kilograms and an initial temperature and an initial temperature of 95 Celsius degrees. Celsius degrees, period. The substance is then, hold on, is then dropped and drop. Okay, is then dropped into a calorimeter. Okay, into calorimeter. Made of aluminum. Made of aluminum. Made of aluminum. Containing containing 0.285 kilograms of water. Okay, of water initially at 25 Celsius degrees, period. The mass of the aluminum container, the mass of aluminum container, okay? The mass of the aluminum container is 0.15 kilograms. Period. Sorry, comma, no period, comma, sorry. And the temperature of the calorimeter and the temperature of calorimeter increases to a final equilibrium temperature to a final equilibrium temperature of 32 Celsius degrees. So calculate period. Calculate the specific heat of the substance. Okay, this is going to be the second one, the second problem. All right, okay. In this situation, guys, it's so convenient trying to working or studying to apply the data. See, as soon as you can see a difference with the last problems that we solved in the last classes. This case, we're talking about three bodies or three circumstances. For example, we're talking about the substance. Okay. We're talking about the aluminum. This is the calorimeter. And we have the water. Three circumstances, three important things. And we have to apply in these calorimetry principles or thermal equilibrium. All right. So that's going to try to regroup every data. We want to reorder the data. Okay. For example, the mass of the unknown systems, because we don't know what it is, will be 0.125 kilograms. Okay. And initial temperature. Remember, when we're talking about initial temperature, in this case, we won't say, TO. No, not necessary. Because the initial temperature in this situation is 95 Celsius degrees. Remember, 95 Celsius degrees. If you compare with 25 and 32, this is going to be the highest value of the temperature of the system. So we're going to add the value TF. That will be 95 Celsius degrees, okay? And according for the situation, the equilibrium temperature of the system will be, 32 Celsius degrees, all right? And what we're looking for the system, we're talking about what will be the value of their specific heat. We are regrouping those values. Well, let's going to talking about with the aluminum. What is the mass of the aluminum? The mass of the aluminum container is 0.15 kilograms. And because at the beginning, the aluminum is containing the water. For that reason, the water and the aluminum has the same lowest temperature at the beginning of the system. That will be 25 Celsius degrees. We know the equilibrium temperature 32 Celsius degrees, and we know what will be the specific heat of the aluminum. And the specific heat of the aluminum will be, give me a hand with you. Specific heat of the aluminum, please.
The specific heat says
Mhm.
900. 900.
900.
Yeah.
Only
joules
900. Okay.
Mhm.
Okay, 900 joules kilograms Celsius degrees. All right. This is the value from the aluminum. And now let's going to talking about the water. With the water, the mass of the water will be 0.125 kilograms. 0.125 kilograms. And because the water is inside the container of the aluminum, both have the same values. I mean, the lowest temperature of 25 Celsius degrees and the equilibrium temperature will be 32 Celsius degrees. And the specific heat of the water, that will be 4,186 joules per kilograms Celsius degrees, right? We are arranged those values. We arrange the data. Now we are fully prepared to solve this problem. Remember, the postulate of calorimetry, that will be the quantity heat that we're supposed to gain or lost, going to do over here, the quantity of heat that we're supposed to lose, that will be the quantity of heat that we're supposed to gain. Okay? Who is going to lose or lost the quantity of heat? Always the body of the substance who has the highest temperature. For that reason, that will be the substance. So at the moment when to apply the equation, I'm going to say MS, S represents the systems, the specific heat of the substance, and the value will be TF minus TE. I mean TF 95 Celsius degrees minus 32 Celsius degrees. And we have the equation, the quantity of heat lost by the systems. In this equation, that will be equal to the mass of the aluminum, specific heat of the aluminum, and because the aluminum is gaining heat, will be the difference between the equilibrium temperature minus the initial temperature, I mean the lowest value of the temperature, will be 25 Celsius degrees. And how about with the water? The water is is gaining heat, right? For that reason, I'm going to add the mass of the water, a specific heat of the water, and same way over here, right? 32 Celsius degrees minus 25 Celsius degrees. All right, this is going to be the calorimetry or the thermal equilibrium equation. Now let's going to replace the values. For example, sorry, the mass of the water is 0.285, right? Sorry, I'm going to fix this one. 0.285 kilograms, the mass of the water. Okay, let's see. 0.125 kilograms, specific heat systems. And what will be the difference between 95 minus 32? Will be 95 minus 32 will be 60 what? 60 what? 63. Come on, guys, give me a hand. Okay, 63 degrees equals the mass of the aluminum, 0.50 kilograms. The specific heat of the aluminum, in this case, will be 900 joules per kilograms Celsius degrees. And 32 minus 25 is 32 minus 25, 7 degrees. Okay, 7 degrees, perfect. Plus the mass of the water, okay. Yeah, 0.285. 0.285 kilograms. The specific heat of the water will be 4,186 joules per kilograms Celsius degrees, and the difference between will be 7 Celsius degrees, right? Now, give me a hand. Please multiply 0.125 times 63.
7.875.
7.75,
875.
okay, kilograms Celsius degrees equals. All right, 0.15 times 900 times 7. 0.15 times 900 times 7.
94,500.
94,500.
500.
That will be obviously used. Plus another one, 0.285 times 4,186 times 7. Zero point 285 times 4,186 times 7. Come on, quickly. Come on, you can do it. Come on, you can do it. Come on, you can do it. Do it, do it,
Mr.
do it.
4,000 what, Mr.?
4,000,
156.
4,186. Yeah.
Ah, okay,
Zero.
86.
Okay. 0.285 times 4,186 times 7. And will be. A ver, usen la calculadora, muchachos. Mire que los voy a hacer venir aquí, se los prometo, que para el examen los voy a traer acá y por Dios, lo juro por Dios que los voy a hacer en el calculador, sin calculadora, ya que no la quieren usar. A ver, la cuenta de 3, quiero la respuesta. 1,
8,
ajá, 8,
8,291.22.
ok, 8,200,
91.22.
ajá, 0.22. Ok, all right, seguro, 8,291. Pero están seguros que este es 94,500, 0.15 por 900 por 7. ¿O será que yo escuché mal? 0.15 por 900 por
Sí, no,
7.
es 945.
Ah, ¿es 945 o 94,500?
945.
Ah, ya decía yo, pucha, qué raro. So, gracias, gracias. 945 joules. Okay, now we have to solve for the specific heat. There will be the addition between 945 joules plus 8,291.22 joules. First add, and after that divide 7.875 kilograms Celsius degrees. So please give me the answer. Primero sume lo que está arriba. Después cuando ya tiene el total, lo que le dé entre esto, pero primero sume. ¿De acuerdo? Okay, and the answer will be 'Ya veo yo que quieren que los traiga acá y lo voy a hacer, que me hagan un examen.
1172.85.
Bueno, 1172 punto.
85.
Ah, bueno. Joules per kilograms Celsius degrees. And this is going to be the answer of the problem number 2. Okay? Remember, when we're talking about the quantity of heat or the thermal equilibrium, no will be necessary one system equals to another one. It could be 1 equals the addition between two systems, or could be 3 equals the addition of 4 substances, and so on. All right. Now, we're going to talking about obviously applying the thermal equilibrium, but this case, what we're talking about, that change of phase. I know you studied that already in the chemistry class, okay? And according to Ms. Avelar, you're expert in the material, right? You know how to do that. She said, oh, the 11th grade students, this is okay. This is like if we multiply 1 times 1. So it's a good information to me. For that reason, I'm going to do it. Quickly method, right? Are you agree with me or no? Huh? Is that true? Ms. Avelar said that one. Is that right or is that a liar? Huh? I think that was true. So excellent. So I'm going to explain it in a few minutes, and that's it. I'm going to do a little review. The change of phase. Okay, guys, change of phase. In the change of phase of the materials, in these materials, guys, uh, we have we have to kind of quantity of heat in this situation. The quantity of heat of fusion and the quantity of heat of evaporation. So in this case, we're talking about two kind of formulas. Q,
Mister,
ajá,
cuando termine con ese tema, ¿será que puede mandar fotos de la board del lado, del tema de que vamos a terminar y las dos?
vale más que me lo dijo, que no se me ocurrió borrarlo, si no, olvídese.
Sí, por si
Ok,
acaso le digo a Mister de ahorita.
bueno, pues
Gracias.
vaya. So, we have two formulas. Q equals MLF and Q equals MLB. All right, where the M represents the mass, Q represents the quantity heat, and LF represents the fusion latent heat, and the LB represents the vaporization latent heat. Okay, for that situation, you have to obtain at the raise your hand, please the table 11.2. The table 11.2, let me see, is is located in the page number, hold on a second. Yeah, in the page number 370, right? 370. This is you're going to find out the latent heats of fusion and vaporization for the systems. Okay, I'm going to give you the latent heat of water, the fusions and vaporizations. For example, if we're talking about water, and I'm going to label water. Okay, the value for the latent heat of fusion of the water, water will be 3.33 LF, 3.33 times 10 at the fifth power, water, yeah, fifth power joules per kilograms. Joules per kilogram. This is not specific heat. And if you want to use the calorie, 79.7 calories per grams. Okay, this is the values, the constant values for the latent heat of water. And what about with the vaporization heat of water? Okay, the vaporization heat of water will be 2.26, I mean LV, 2.26 times 10 at the 6 power joules per kilograms. Joules per kilograms. And obviously in calories, there will be 540 calories per grams. All right. This is the constant value of water, water. Okay. And please, guys, and at the moment, we're going to solve your exam. Be careful when you read this latent heat because this is not the first time, and I think that this is not going to be the last one. The students made a mistake. For example, when we're talking about well, actually, I don't think that that's going to happen because this is an English class. However, in Spanish class, when we're talking about the latent heat of fusion with the ice, in Spanish, ice is yellow in Spanish. but there is a latent heat of helium. Helium. And I don't know why, but some of my students a few years ago, instead to use the data from the ice, they're using the latent heat of helium because they're confused hielo con helio. That's why I'm requesting, please, please, please read before applying the values, okay? So what we're going to do, this situation, we're going to apply, obviously, the calorimetry, the principles of calorimetry, applying the latent heat and phase change, right? Or change of phase. But remember, the first thing that we have to do is determine how much energy is required to transform one singular substance to another one. And I think the time is out, right? It is a 1:10 p.m. Okay, we're going to finish the class of this part. And the another one, we're going to start for the change of phase, calculating the quantity of energy for one body passes to another one statement, for example, solid to liquid, liquid to gas, and after that, applying the principles of calorimetry. Please take a photocopy, take a screen. I don't know what you have to do, but please have the reach of your hand, the tables 11.1 and 11.2, all right? So thank you so much for your attendance. Have a great and wonderful day, all right? Take care
Thank
of
you,
yourself.
Mr.
Have a nice and wonderful day. See ya.
Bye.
Bye bye.